Okay, let's continue. Well, one of you pointed out that this is not a force, but it's a force per volume. It's completely right. As long as we only looking for comparing forces or looking for the sign of the forces going up and down, actually it will not matter. So, excuse me, please. This is not a force, but a force per volume. But it will not matter because we are only looking whether for the direction of the force and compare two quantities most where the dimension is equal. So this will be valid despite this is not a force but force per volume. We convinced ourselves how the change of the density of the surrounding goes. It's d rho by dr times delta r. What about the change of density of the element? And to derive the change of the density of the element, we have to introduce some assumptions. The first assumption is that the motion of our fluid element or our mass element proceeds in pressure equilibrium. That means that the change of the pressure within the element is equal to the pressure change of the surroundings, or alternatively or equivalently, if the change of the pressure within the element is equal to the change of the surroundings, then of course the pressure of the element is equal to the pressure of the surroundings. So the motion of our material proceeds in pressure equilibrium with the surroundings. It's an assumption that the pressure within the element is equal to the pressure of the surroundings. The second one will be that the changes of state within the element will be adiabatic. That means if it's supposed to be adiabatic, then the pressure within the element will depend only on a single other thermodynamic quantity, which we choose to be the density of the element. Adiabatic means entropy is constant, and therefore one of the it's only a single parameter which the other quantities depend on. We can write it in terms of pressure as a function of temperature or pressure as a function of density. So we can write the P of the element is pressure of the element only a function of the density. Or rewrite it in terms of the change of the pressure in the element. dP of delta P of the element is then simply the derivative of pressure with respect to density times the change of the density of the element. And this derivative of pressure with respect to density, according to our assumption, is to be taken at constant entropy or adiabatically. That means this can be written in terms of the so-called gamma adiabatic, which is one of these logarithmic derivatives appearing in thermodynamics. Gamma adiabatic is defined as d log p by d log rho at constant entropy, purely thermodynamic quantity, no reference to any stellar model. And then this might be written, dP by d rho adiabatic is written as the gamma adiabatic. This is the adiabatic index times the pressure over the density. Okay, I expected your objections. How can we assume pressure equilibrium and adiabatic state changes of state? Adiabatic changes of state means the displacement or the changes of state have to be sufficiently fast, so fast that the element cannot exchange heat with its surroundings. Otherwise, if it exchanges heat with its surroundings, it would not be adiabatic. This is the condition for adiabaticity. So it has to be sufficiently fast. What is required for the element to be in pressure equilibrium with its surroundings? what would be required. So this means you have to consider fast changes. And here it should proceed slowly. Otherwise, if it proceeds fast, then we have accelerations, and then we do not have mechanical equilibrium, pressure equilibrium for the element. So this assumption implies we have slow motions, long time scale. This assumption means we have fast changes of state. Well, this seems to be a contradiction, or so it's a bit difficult to get out of this contradiction. Well, you get out of the contradiction by considering this is the thermal time scale on which this should. Here you compare changes with respect to the thermal time scale, and here the time scales which you have to consider is the mechanical time scale. So, but you have to keep in mind this. Here you have to be slow compared to the mechanical time scale, and here you have to be fast with respect to the thermal time scale. There may be no gap between these conditions, and then your theory fails. But this is only valid if there is a gap between mechanical timescale and thermal timescale. And if this gap is sufficiently fast, we find some way in between where we can meet both of these requirements. So keep in mind, slow with respect to the mechanical timescale and fast with respect to the thermal timescale. Okay, well, now we can use these assumptions to formulate our to calculate the delta rho of the element. That's what we are aiming at. Well, first of all, we know delta P of the element is equal to delta P of the surroundings because there is pressure equilibrium. This was one condition. Then we know that for adiabatic changes of state, delta P of the element can be expressed in terms of the delta rho of the element. So this is gamma adiabatic times P over rho times delta rho of the element. And of course, similar as the delta rho of the surroundings, we can also express the pressure change, delta PS of the surroundings, by the pressure gradient times delta R. So that of the surroundings is given by dP by dR times delta R. It means we can now express delta rho of the element in terms of delta R. We go from the very left side to the right side. We express delta rho of the element in terms of delta R. And we can now take these together. Well, delta rho of the element is simply dP by dR times 1 over this factor. This is rho over P times gamma adiabatic. And the delta rho of the surroundings was d rho by dr. And this bracket has to be multiplied by the gravity minus g. Let's go back to see. This was the force, or the force per volume was minus g times delta rho. Delta rho was delta rho E minus delta rho S. Delta rho S was density gradient times delta R. And combining all this together, we are left with the force is minus gravity times, this comes from delta rho E and this comes from delta rho S. So we are left with force is minus gravity times these bracketed terms times delta R. Now, if we make delta R positive, we move it up, then the force should point downwards. So for stability, this is already a minus sign. For stability, this bracketed term has to be positive, and if it's negative, then the force points in the same direction as the displacement. We have an unstable situation. So the sign of this bracketed term will determine whether we have a stable stratification or an unstable stratification. So Now we inverted here this, I have taken out this, or put in the minus here. So this quantity positive means stability. So this quantity negative means stability. So we take it in that form. Density gradient minus rho over gamma adiabatic P times dP by dr smaller than 0 means stability, and bigger than 0 means instability. So this is one form to formulate the criterion for instability or stability with respect to the onset of convection. So it depends on pressure gradient and density gradient whether our configuration will be, our stratification is stable with respect to perturbations, and this means we have a criterion for the onset of convection or with respect to this stability against convection. Okay, now maybe someone who is familiar with fluid mechanics, or it's also part of elementary physics. We have one form of instability of stratification is Rayleigh-Taylor instability. What is it? Well, the simplest case is you have water and oil. If you put water, if you have oil and try to put water very carefully on top of it, then if you perturb it a little bit, water will go down and the oil will come up. This is Rayleigh-Taylor's instability. If it's stable only if the denser fluid is at the bottom and the light fluid, less dense fluid is on top. So you have to place, with respect to gravity, the less dense fluid, less dense material on top and the dense material on the bottom. If you invert it, then it will change and the denser fluid will come down and the oil or the lighter fluid will come up. Okay, now let's assume within our criterion that our fluid is incompressible. That means incompressible means that the change of the density of the element is 0. Then it's not compressible. It will not change the density. What happens then? Delta rho, go back. Delta rho will be equal to minus delta rho s, because delta rho, the element, if it's incompressible, it doesn't change its density. So what happens to the stability criterion? Well, then the stability criterion, or the force which the buoyancy force is then given by G times delta R times d rho by dr, which is simply the change of density of the element. That means the instability is controlled only by the gradient of density. And that's what we observe. If the density gradient, if the density decreases upwards, it's stable. If it increases, it's unstable. So the sign of the density is responsible for this instability. So Rayleigh-Taylor instability, in principle, what we see here rely on the same physics. The only approximation we have done is considering the element either compressible or incompressible. But that's something which is controlled by the properties of your matter which you consider, which is not controlled by the physics in some sense. So it's only the density gradient of the surroundings which matter. And in the other case, we have also the pressure gradient to be considered. Now let's look at the stability criterion. Well, once we drop this term, we end up with Rayleigh-Taylor instability. This is only achieved if we require that the motion of our fluid element is incompressible. So the criteria are essentially identical, they're simply differing by this term. So how can this term disappear? Pressure gradient is, cannot do anything about that. But what about this quantity here? Actually, what is it? How can you interpret this quantity? front this factor here. No, that's difficult to do. Well, essentially you are right. You can also make gamma adiabatic going to infinity, but let's consider the change of pressure dp by d rho. That's where this comes from. This is well, dp by d rho is no, p delta p is equal to dp by d rho. Keeping constant something can be adiabatic or temperature, also delta rho. So what happens if you compress fluid? You exert some pressure on your fluid element. How will the density react on that? If this factor is large, then the density change is small, needs to be small. That means if this quantity goes to infinity, then you have delta rho automatically equal to 0. But what is dp by d rho physically? dp by d rho is gamma adiabatic times p over rho. How do you interpret this quantity physically? It is the speed of sound. So this is sound speed squared. So if you let the sound speed go to infinity, then this term vanish and you will have, you're left with d rho by dr and you're left with Rayleigh-Taylor's criterion. So it means if you have high sound speed, then this term will no longer matter. For instance, example, if you compare air and water, water is essentially incompressible, and it means, or you can also express it in terms of sound speed. The sound speed in water is much higher than that within the earth. So water behaves incompressible, and therefore this factor in front of dp by dr will be small compared to the density gradient here. So what we learn from that this criterion was derived on the basis that we consider compressible motion, which in the limit of incompressibility, namely high sound speed, reduces to the criterion which is appropriate for incompressible fluids, and we end up with Rayleigh-Taylor's criterion. So there is actually no physical difference between the two criteria, and they should not be used at the same configuration to compare or to distinguish between different phenomena, because either our material is compressible, then we have to take into account this term, or the material is incompressible, then we don't need to take it into account. But this is the superior criterion, which reduces to the Rayleigh-Taylor criterion in the case of very high sound speed or in the case of incompressibility. What you see here is also incompressibility goes along with the run of the sound speed. High sound speed means that the flow or the fluid behaves incompressibly. Low sound speed, then we have to take into account pressure gradient, and the flow is no longer, or the motion is no longer incompressible. So what we learned from that, the criteria cannot be used simultaneously in the same situation, because either the Rayleigh-Taylor criterion is correct or the other criterion is correct. But you cannot say, well, I consider the same system once with the Rayleigh-Taylor criterion and the other time with the complete criterion. You should, the sound speed will control which degree of approximation you will consider here. This is the same physics, only with different properties of the matter. So the properties of matter control which criterion you have to take. Physically, there is no difference. Criteria must not be used simultaneously. I'm emphasizing on that because you find in literature that people considered stability with respect to the onset of convection. And then they saw, oh, well, there's a configuration arising which we don't want. For instance, should comment on this in more detail because it seems to be not known to many astrophysicists. Well, usually you have a monotonic behavior of both temperature and pressure. So pressure decreases from inside to outside. That is caused simply by gravity. Gravity forces that the pressure has to increase monotonically inside from the surface to the center. The same is true for the temperature, because temperature gradient controls the heat flux. If you would have a temperature inversion, if the temperature would not go monotonically, then you would have a flux reversion. The flux would reverse. If you have a positive temperature gradient, then the heat would flow into the flux. This cannot happen, so we have only outgoing flux. That means the temperature gradient has to be negative. There must be a decrease of temperature from the very center to the surface. But what about the density? The density in general also decreases with radius. The density decreases, but there may be some regions within the star where it does some strange things. It goes like that. This is a so-called density inversion that occurs in many stellar models, even on very normal and non-exotic stellar models. And some people don't like this density inversion. So actually this happens in the vicinity of convection zones. You have to have a convection zone to get this strange behavior of the density inversion. Here the density increases with radius. And I say, okay, we have determined the property of the convection zone using the full criterion, taking into account the compressibility of matter. And I see this strange configuration. They don't want to have this density increase. So what they do, they say, well, we don't want to have it because it is Rayleigh-Taylor unstable. And this is the wrong concept, I think, because either you take the properties of the matter correctly into account, then you have to include the pressure gradient. You cannot go determining the properties with the full criterion and then afterwards, I don't like this situation. I see there is a density inversion. This is Rayleigh-Taylor unstable. It is the same physics. Either it is controlled by both buoyancy and the properties of matter. So it's not, the argument is not correct to say this is Rayleigh-Taylor unstable, and therefore we need to consider it in a different way. The argument is not correct because it might be true that convection, if you treat convection in a different way, that you get rid of this density inversion. But the argument that the Rayleigh-Taylor criterion tells you that such situation is unstable is not correct. Once you have a situation where pressure gradient has to be included in the stability criteria. Okay, that's often an argument to get rid of this density inversions. Say, well, this is Rayleigh-Taylor unstable. This argument cannot be used here. Okay, so now to arrive now at the criteria which are common in astrophysics. This is not the common form of the stability criterion. Some people actually use it, but it's not the form in which the criterion for convective instability is used in general. So let us derive the criteria, the stability criterion in their common form from the criterion we have found. So the quantity Q, this was d rho by dr minus 1 over sound speed squared times dp by dr, needs to be smaller than 0 for stability and bigger than 0 for instability. How do we derive from this criterion the standard form of the criteria for onset of convection, which is Schwarzschild's criterion and Ledoux's criterion for these are the criteria which are used in standard stellar physics. Well, the connection to the standard criteria are given by the equation of state. We simply reformulate this criterion in terms of the thermodynamic basis, pressure and temperature, rather than density and pressure as derived here. So what we have to do, we have to replace density and pressure by pressure and temperature. And in the case once we have also as a parameter the chemical composition, then this equation of state also needs to take into account the molecular weight. So if we have chemical variation in chemical composition, then we have to introduce chemical composition or the mean molecular weight as a third parameter. Now, if we take the differential form of this equation, we have the logarithmic derivative of the density will be expressed in terms of the logarithmic derivatives of the pressure and the temperature, well-known coefficients alpha and minus delta, plus a logarithmic derivative with respect to the chemical composition or the mean molecular weight, and let's call the logarithmic derivative of density with respect to the logarithmic derivative of density with respect to mean molecular weight by phi. So we take this form of the differential equation to replace the density gradient in our stability criteria and see what's left then. Okay, then our quantity Q, which controls the stability, might be written in the following form. We take the logarithmic pressure gradient out of the brackets, we take the density out, and we take the delta out of the brackets. Then we are left with, well, this is simple algebra. I think you can, if you want to convince yourself, you can do this simple algebra yourself. We are left with 1 over delta times alpha minus 1 over gamma adiabatic. That is, of course, coming from this term here. This 1 over gamma adiabatic comes from here. The other ones comes from the d rho by dr and its replacement by pressure gradient and temperature gradient. The last term comes from the gradient of the chemical composition. So by taking out the logarithmic derivative of pressure, we have here the logarithmic derivative of temperature with respect to pressure left. That's done by or achieved by taking out the logarithmic derivative of pressure with respect to radius. And here we are left with the logarithmic derivative of the mean molecular weight and the pressure, and we call this nabla mu. This is a new quantity. Now, these two quantities are related to an actual stellar model. So they refer to the temperature gradient and the gradient of of mean molecular weight. Therefore, this is based, or this has to be regarded as a derivative which is taken for a specific stellar model. Therefore, this is nabla, our definition of nabla, and this is the newly introduced nabla mu, also referring to some stellar stratification or some stellar model. Okay, now the condition that the sign, well, dp by dr is negative, delta is positive, so this is a negative quantity, and the sign, the discussion of the sign with respect to stability or instability then leads to the following inequality. That means nabla has to be smaller than this quantity involving gamma adiabatic and the other coefficients of the equation of state, plus phi over delta times nabla mu. For stability, nabla is bigger than this right-hand side. the case of instability. Well, yeah, for radiative transport, we have nabla is equal to radiative value if the energy is transported by radiative diffusion. And once this nabla radiative is bigger than the right-hand side, we know we have instability, convection sets in. Otherwise, we have stability and we have no convection. Now, this combination of the derivatives, the various derivatives, thermodynamic derivative can be given a much simpler form, because once you can write 1 over gamma adiabatic, you can rewrite in terms of alphas, deltas, and the so-called nabla adiabatic. Nabla adiabatic was d log T by d log P at constant entropy. So using the equation of state, 1 over gamma adiabatic was d log rho by d log P at constant entropy. Now we replace log rho by the equation of state. This is alpha times d log P by d log P at constant entropy. This is 1, of course. And second one is d log T by d log P times minus delta. So this is by definition nabla adiabatic. So 1 over gamma adiabatic is alpha minus delta nabla adiabatic. Keep in mind, gamma adiabatic and nabla adiabatic are determined only by the equation of state. No stellar model is involved here, whereas in the comparison above, we have to insert a particular stellar model. This refers to the gradients, the actual gradients within the star of temperature and pressure. Now, by this relation, we can simply write this term in terms of nabla adiabatic. It's simply nabla adiabatic here. Okay, so this quantity here is nabla adiabatic from this relation, and we are left with the following final criterion. Nabla radiative is smaller than nabla adiabatic plus the term involving the gradient or the nabla of mu, nabla mu. For stability, nabla radiative has to be bigger than this, or is bigger than nabla adiabatic in the case of instability. Well, this is now the more general form of the instability criterion. This is so-called Ledoux criterion, involving also, or taking into account also, the variation of the mean molecular weight. It's called the Ledoux criterion for nabla mu not equal to 0, and it reduces to the so-called Schwarzschild criterion in the case of nabla mu equals 0. So it's a very simple form. Nabla bigger than nabla adiabatic means instability. Nabla smaller than nabla adiabatic means stability in terms of the Schwarzschild criterion. And if you want to take into account chemical composition variation, then you have to resort to Ledoux criterion. So what you see is Rayleigh-Taylor's criterion, Ledoux criterion, Schwarzschild criterion are based on the same physics. They come about because the situation considered, because the matter considered is either incompressible, you end up with the Rayleigh-Taylor criterion. If you have no chemical composition gradients, you end up with the Schwarzschild criterion. If you have chemical composition gradients, then you end up with Ledoux criterion. There is no secret behind all that. It's all based on the same consideration. It's simply the matter, the matter or the properties of matter, which distinguishes between these three criteria. So you are forced to take one of these, or to select one of these by the properties of the situation you consider. Then you have no choice. Okay, and in particular, you must not apply two different criteria at the same time. and draw different conclusions from it, because you are forced to take one of these, and that's it. Okay. Well, I haven't gone through, haven't proved this explicitly, but the general form, the most general form for this stratification instability may be written in terms of the entropy gradient of this situation. If the entropy gradient, the S by the R, is bigger than 0, so if the entropy increases outward in a star, then you have a stable stratification. If it decreases, you have an unstable situation. This is the most general formulation and also the simplest formulation. So if you calculate the entropy, the specific entropy, and it increases outward, you have stability with respect to convective motion. And if you have instability, then if the entropy gradient decreases. The physical origin of this instability, keep in mind, is buoyancy. There's nothing, no other effect involved. And as a cautionary remark, criteria should not be confused. Application depends on the particular situation you consider. The physics is always the same. Okay, sorry, this was a little bit exhausting, I think. But you can consider all these different criteria with respect to one point of view. Its buoyancy, and the mechanism to derive it is exactly the same in all these cases. Okay, now we have considered the onset of convection. We have considered the stability criteria. Now we would like to know what happens then. Once the stratification is unstable, the matter starts to move. You have convective motion, and this gives rise to convective energy transport. How do we describe convective energy transport? And this is the big problem in astrophysics. There is no consistent theory of convection so far, and even the simulations might not be used or are not useful as a theory of convection, because most of the simulations, or if they are done correctly, then they have to involve a theory of the smallest scales appearing, because in a simulation you can only resolve the big eddies, the big mass elements moving up and down. You have limited resolutions, so you need to resolve or need to have a theory for the small scale convective elements, because you cannot resolve them. If you do the calculations without this, without an additional theory for the smallest scale, you may get an explosion of your perturbations, and this is not true. It's known in fluid mechanics that you have to invoke, or you have to resolve, account for the dissipation in the small scale, on the small scales, by using additional prescriptions for small scales. Okay, so it's a pity that even numerical simulations cannot really help you much. Perhaps some advance will be reached in the next few years. Well, I'm a bit critical and pessimistic about that, but keep in mind there is no consistent theory of convection. Even you have to be careful once you consider numerical, or once numerical calculations are presented. They have to be done very careful and with a high degree of sophistication. Otherwise, the results are not really meaningful. The problem is we have reduced the problem now to calculate the value of nabla, which is the actual temperature gradient in terms of d log T by d log P. Well, there are some limiting cases where you can argue how big the value of nabla should be. Okay, so the convection sets in when the when nabla radiative becomes bigger than nabla adiabatic, according to Schwarzschild's criterion. So what will happen? We have a big temperature gradient, and this big temperature gradient is too big to be stable. So what convection will do, it will reduce the origin of the instability. So what it will do, it will reduce the nabla, it will make it smaller. We start from the radiative value, which is bigger than nabla adiabatic, and it will reduce it to a value below nabla radiative. How big can the reduction in nabla be? How big can the reduction in nabla become? Can it become below nabla adiabatic? We have three values: nabla radiative, nabla adiabatic. Nabla radiative is bigger than nabla adiabatic, so it reduces the actual value, the final value of nabla below this value. But can it reduce even further down below nabla adiabatic? What would happen if nabla is below nabla adiabatic? Then it would meet a stable situation. So then the convection would cease and there would be no convection anymore. So the maximum value or the maximum reduction will be nabla goes down to nabla adiabatic. So we have the result that in the finally nabla should be between nabla radiative and nabla adiabatic, some value in between. And the question then is, where between nabla adiabatic and nabla radiative is nabla finally? Well, if convection is very efficient, then it will reduce it down to the value of nabla adiabatic. It means convection transports energy efficiently, and this again means we have the maximum reduction of nabla close to the value of nabla adiabatic until the marginally stable state is reached. So in this case, we will have, once convection sets in, nabla equal to nabla adiabatic, and this means the convection is in that case adiabatic. It's called adiabatic convection. Well, in general case, the convection is inefficient, and this is called non-adiabatic convection, and it requires some theory of convection. And so far, I told you, there is no consistent theory, and we have to rely on the so-called, the most advanced theory, in question marks, is the so-called mixing length theory, which I regard as a very, very very plausible summary of assumptions. They are physically certainly very plausible, but it's some kind of engineering prescription. It's not really a theory. There are many separate assumptions which are plausible, which are physically plausible, but which cannot be regarded as a real theory. Mixing length theory, it's called mixing length theory because the parameter in this theory is the typical mean free path of a convective element, which is taken to be of the order of the dimension of a convective element. So this mixing length is the parameter of the theory. There is a parameter which tells you how, or which measures the length, this mixing length in terms of the pressure scale height within your configuration. So the pressure scale height is something like 1 over P times dP by dr to minus 1. This is the so-called pressure scale height. It's a length scale which is associated with the stratification of pressure. And the mixing length is measured in terms of the pressure scale height. So the mixing length is, say, some people take 1 pressure scale height for the mixing length. Some people take 2 pressure scale heights. Usually people take some value in between, 1.5 pressure scale height for the mixing length, and the mixing length is a measure for the mean free path of a convective element, or alternatively of the dimensions of a convective element. I will not go into the details, but this mixing length theory will in the end give you a value, or will provide you a value for nabla between nabla adiabatic and nabla radiative. Of course, if you go to the stellar core, when the specific heats, or not the specific heats, the heat capacities are large and the matter can store heat efficiently, then nabla will be close to nabla adiabatic. And if it's only weak instability, then nabla will be close to nabla radiative. But the precise value will be provided then by mixing length theory. Keep in mind, it's not a real theory. It is a summary of plausible physical uh, estimates, and it's not really cannot really regard it as a real theory from stellar evolution. Okay, now once we have commented on uh, energy transport, on nuclear energy generation, opacity, now we might be able to calculate stellar models and calculate stellar evolutions. Okay, concerning the mathematical problem, stellar evolution is so-called mixed initial boundary value problems, because we are at the boundary have at the center we have certain boundary conditions to satisfy, which is, for instance, luminosity is 0 at the boundary at the center, then the mass is 0 at the boundary, and it decreases to the actual value of the mass and the actual luminosity seen the star. So we have to satisfy certain boundary conditions. That means in terms of the radius as a dependent variable, the radius has to be 0 at mr equal to 0, and also the luminosity has to be 0 at the core of the center of the star. Then there are surface boundary conditions. When surface boundary conditions is that our outer boundary is actually the photosphere of the star, and the photosphere of the star is defined by Stefan Boltzmann's law. That means the temperature there is equal to the effective temperature, and we have the relation between mass at the outer boundary, L at mr equal to m, should be equal to the radius squared at the outer boundary times the temperature squared, temperature to the fourth at it's only the boundary of our model. It's not the boundary of the star, because we have to take, for the entire star, we would have to take into account the stellar atmosphere. Here, it's the outer boundary of our model, because our models are usually restricted to those parts of the star which are optically thick and which lie below the photosphere. Okay, there is a second. We need, of course, this is a is derived from considering or estimating the properties of the atmosphere, from integrating from infinity to the position where tau, where the optical depth is equal to 2/3, and then we end up by this estimate for a prescription of the pressure at the outer boundary, which is given by the discussed this in detail at the beginning of this section, and usually the outcome or the properties of stellar evolution are discussed in terms of the Hertzsprung-Russell diagram, plotting the luminosity against the effective temperature. Well, for either by going through stellar evolution and then selecting one model determined in the numerical way, selecting one model and considering its stability. There, for stellar um, pulsation problems, we can do a restricted problem, because the problem is, once you use stellar evolution, then you will have a stellar evolutionary track. You start is observed. Usually, you have to fine tune your initial conditions to go through a position in the Hirschsprung-Russell diagram where a particular star is observed. You can shorten this stellar evolution calculation by considering a so-called envelope problem or envelope solution. Then you disregard the solution and you determine the luminosity and effective temperature. This is determined by the observation, and you possibly also have some information on the mass. And so you have three parameters available. You estimate the mass and you have the position in the HR diagram. Then you have three parameters. You disregard the nuclear processes and you exclude the stellar core, all these the stuff connected to nuclear energy production and so on will be disregarded, and you assume once you disregard nuclear processes, you automatically assume that your chemical with mass. Keep in mind dl by dmr is given by the nuclear energy generation. If you disregard this energy generation, the gradient of luminosity. So you don't need to integrate this equation. How is then the envelope, the structure of the envelope? Miss some here. Okay, then you consider the already solved. You keep luminosity constant. You have mass conservation. You have hydrostatic equilibrium. And you can now solve the equations by an initial value integration, contrary to the boundary value integration. Stellar evolution, you can now integrate from the surface towards the center, stop at some point, and you some point where you cut your integration as an initial value from the photon temperature and the mass. Okay, let's consider hydrostatic model as a means for studying stability with respect to. Okay, let's now consider some typical diagram for stellar evolution. I should make this a bit smaller here. Okay. Evolution starts on the 0H main sequence. This is point 1 here. This is the evolutionary track, the evolution followed for a 5 solar mass from the very beginning, from the 0H main sequence. 0H main sequence of course, the star has already had some history because it has come from stellar formation, and then it has to settle down at some point in hydrostatic equilibrium. This is at point 1 once hydrogen starts to burn in the center. So while hydrogen is burned in the center of this 5 solar mass object, it goes up that way here. Uh, 10 to 7 years typically. Then you have a contraction phase. The star will contract in its radius, thereby releasing some energy, some gravitational energy. And at this place, the hydrogen is started to be ignited in a shell around the burned, of the Hertzsprung-Russell diagram. It stops at some imaginary line, which is the so-called Hayashi line, and then it performs some blue loops from there. These blue loops are different or vary from mass, from track to track. So it depends on the mass how many loops will be performed, and then on this way through the loops, there are the second burning is ignited in the center. This is the ignition of the helium burning in the center. Then there is a point where the star again contracts when helium is exhausted in the center, and so on. It performs several loops. Once it performs these loops, it several times crosses the so-called instability strip, the Cepheid instability strip, where the stars are found to vary and to be show variability according to the Cepheids or pulsate like the Cepheids are found observationally. So there is a strip where the star starts to pulsate. Whenever it crosses it, then it starts to pulsate as a Cepheid variable. This as an example how this looks like. Well, several loops. The tracks do not overstep the Hayashi line. What is the Hayashi line in the Hertzsprung-Russell diagram? Just in a few short sentences, the definition of the Hayashi line has to do with convection, with energy transport by convection. It's defined by nabla equal to nabla adiabatic for the entire star. So stars on the Hayashi line are defined as completely convective stars. Left to the Hayashi lines, the stars are partially radiative. On the Hayashi line, they are completely convective, and to the right of the Hayashi line, we do not find hydrostatic equilibrium anymore. So this is for static configuration. This part of the Hertzsprung-Russell diagram is forbidden for evolutionary tracks. So to say, if you would go to the right-hand side of the Hayashi line, then we would have extremely strong convection. This convection then operates on the dynamical timescale and pushes the star back to the Hayashi line. This is a boundary for evolutionary tracks. Okay, what can we say more for stellar evolution? Well, here we have a Hertzsprung-Russell diagram of several evolutionary tracks between 1 solar mass and 30 solar mass. Qualitatively, all these tracks are similar. We have this main sequence phase where hydrogen is burned in the center, always this between point 1 and point 2. Then we have the contraction phase. This is the small kink in any of these tracks. Then the star goes very rapidly to the Hayashi line, crosses several times the Cepheid strip, performs, depending on mass, loops or not loops, For the low mass stars, there are no loops. For the high mass stars, there are several loops. Blue loops towards the left of the Hertzsprung-Russell diagram, and here is the imaginary Hayashi line. Okay, that's how stellar evolution usually looks like. Okay, this was just an example how stellar evolution or stellar evolutionary calculations provide an evolution within the Hertzsprung-Russell diagram, and how these evolutionary tracks look like. And now we can, in principle, once we observe a star, a pulsating star somewhere here, then we can try to match some of these tracks to try that the evolutionary track will match the position, take this stellar model to investigate it for pulsations and stability. Or we can perform envelope integration by just taking the position of the star in the HR diagram and determine the properties of the envelope of such a star. This was very gross overview of stellar evolution. I won't go into more details. In the following, I would just comment on some basic principles which are found for stellar evolution, which are important for stellar evolution, and maybe I can also answer the question, why does a star radiate at all? But that concerns some basic principles. This is an overview how stellar evolution might look like. Do I need to stop here? Well, this is a good point to stop here. Well, finally on this digression on stellar evolution, I will comment then on of the basic principles, and they might possibly lead to a deeper understanding why a star evolves, how the star evolves in the way I've shown you, and what are the basic principles behind stellar evolution. Okay, thanks.